please. So we're going to talk about heating systems today. First, this is just you have to remember what the passive house standards were, or to remember or to understand the passive house standards. Why? This is a must. Okay, so again, this is not the goal of this course. We should have done this in 260. We calculated the thermal resistance of walls and roofs and windows, and then when we calculate that, we have to meet these passive house standards. What are the passive house standards? Well, in terms of insulation, we have super insulation. So the walls, roof, and floors should be above 50, the R value. Okay, so it should be above 50. So that means that we need at least from 10 to 15 inches of thermal insulation. So keep that in mind. Sometimes 10 is enough, depending on the thermal insulation. Sometimes we need 15. Okay, so we need something like this of the thermal insulation, and then the internal finish and the external finish. But remember that walls are getting thicker if we apply this kind of passive house standards, because the R value should be very high. Then ventilation, we need a heat exchanger. Okay, so to meet the passive house standards, ventilating by opening a window or by doing what we have done so far, just getting the air handling unit and just getting fresh air from outside without the heat exchanger, it's not an option if we want to meet the passive house standards. Okay, so we need a heat exchanger. If we have a single family house, we will have one of those, the heat exchanger we have over there. If we have a commercial building, we need air handling units with heat exchangers. Okay, so it's not an option. And here we have a limitation for the air changes per hour in residential buildings. They don't talk about commercial buildings. Passive house standards work better with residential than with commercial buildings. But anyway, so this limitation applies for residential buildings. For commercial buildings, it will be different. Basically, with commercial buildings, we cannot set a limit in terms of air changes per hour because it depends on the number of people. So we can have commercial buildings with thousands of people and commercial buildings with 20 or 50 people. Okay, so but in single family houses, we don't have thousands of people living together in a single family house. At least it's not convenient. So these are the requirements in terms of R value for walls, the U value for windows. We know that there's a relationship between the U value and the R value. U equals 1 divided by R. But for windows, we don't have the R value. In catalogs, we usually have the U, the thermal transmittance. So it has to be below 0.12. That means triple glazing probably argon field and low emissivity. Okay, triple glazing, argon field, low emissivity. Without this, this is a window. Without those requirements, we can have a U value below 0.1. Okay, we know what triple glazing is. Argon field means that the cavity that we have between two glass panes, air is not enough. We need to fill it with argon. Argon, it's an inert gas. And low emissivity, it's a coating. It's something invisible, so we don't see it, but it performs really well in terms of energy savings for this. Okay, so that's it. In the case of the walls, we need 10 to 15 inches of thermal insulation. In the case of a window, we need triple glazing with argon and low emissivity coatings. And in terms of ventilation, we need a heat exchanger. Okay, so if we do this, just memorize these kind of things. We don't need to think. So the passive house standard is great if you don't want to think. Okay, if you don't abide by the passive house standards and you want to make it better, doing something different, you have to think a lot. So that's very convenient for architects or building designers that don't want to think. Perfect. Abide by this rule. Oh, 15 inches, 15 inches. I don't mind. Triple glazing, triple glazing. Heat exchanger, heat exchanger. So if you meet these three requirements, you are very close to the passive house standards. And then this is more difficult. The annual heating and cooling demand and total primary energy per year. Okay, so this is more difficult because if we have to calculate the heating and cooling loads per year. Okay, so it's the annual or yearly heating and cooling demand. So if we have this 4,755 BTU per feet square. Okay, so we need to calculate the total heating load, and then we have to divide by the area. If we are above this number, it doesn't meet the passive house standards, even though we meet the R value, the U value of the windows, and the heat exchanger. If our building is not well designed, we will have a lot of openings to the north facade, or the orientation is very bad, or I don't know, we have done something wrong in the building design, then we won't have this. Okay, so this is what we are going to do now. We're going to calculate those parameters with the building that we are designing on Fridays. And then at the end, we will see we have it. And what is the total primary energy? Well, the total primary energy, it's a complicated concept. So I will explain this later, okay? So, but basically, if you do this, for this, you don't have to think anything. R value, U value, heat exchanger. And then we will have to check if our building, we have to simulate this a year of our building, and then we have to compare this number, especially this, and this is more complicated because the primary energy, it depends on where the energy comes from. So if we are burning fuel, the primary energy will be different. If we are burning gas, it will be different. Or if we have renewable energy, it will be different. That's it? Yeah, this is it. And if you have a card. I do have a card. Okay, are we all set with it or? Okay. Heating systems. So we're going back because we have had heating systems, not forever, but well, forever. Even cavemen, when they got cold, they just built a fire. Okay, so that's the heating system. In Rome, so in the old Romans, they were a little bit more sophisticated, and they came up with this idea, which is something similar of what we have now with the radiant floor. So they had a kiln or a place made of brick or stone in which they burned fire, wood, mainly, or coal, because they use coal, and then they heat up the air, and then they had this false floor, because they had a cavity between the slab or the foundations, and the flooring and will be the cracks between the tiles, the hot air filter, and then you heat it up. Okay, so it was a sophisticated way to heat up houses, and then you can find this in Pompeii. Okay, so it's not that some guy is making it up. So if you go to Pompeii, Italy, you will find, you know, that this city was very, because the city exploded in the year 100 and something, around 2000 years ago. And the city has been kept as it was, even like people like dying like this, as it was 2000 years ago. So we learned a lot from the Roman way of living, and they had this element in houses and in other buildings. And they had even, they used in other places in which they had hot springs, they used this hot water to heat up the building. So this is the city of Bath in the United Kingdom, close to southwest London. A very nice place, very beautiful. And there was a Roman settlement here, and they found this hot spring, and they created this bath, and they named the city after the bath. Okay, and they used this hot water as a heating system, but they didn't heat up the water; it was heated up naturally. So they okay, so we have not done too much since the Roman times. So basically, we're using the same principles. We have new technology, better technology, but it's not that that different. So we're going to study today what we call the hydronic space heating system. Hydronic, memorize this word, because everything that comes from hydros in Greek means water. Okay, so it can be water, hydronic. We can apply this to any kind of fluid or liquid water. Okay, so when you have this word hydro, whatever, hydronic, hydroelectric, whatever, it means that we are using water. Okay, so in this heating system, in most of heating systems, we use water as the fluid that transports heat. And it's very convenient because the heat can be transported by water. Okay, so we heat up water someplace, and then we have water flow, and then we can transport that heat from the origin to the terminal unit. So these are hydronic systems. What is the principle of hydronic system? We have a boiler or any other source of heat. It can be a heat pump. Okay, so usually we associate hydronic systems with boilers or furnaces, something that burns fuel. But it can be a heat pump as well. And then here we have different circuits. Okay, so we have the outlet, we have the inlet. It's always a closed loop. And here we have different circuits, and different circuits. It can be the first floor, the second floor, the third floor. If we have a few buildings on the first floor, there will be like different circuits, different rooms, or whatever. But it's quite easy. We always have expansion tank. Remember that when we have a closed circuit, we always need expansion tank because we are heating up water, we are changing the volume, so the water will expand, and if it expands too much, there will be that expansion tank. And we have a circulation pump. And then there are a lot of bulbs and a lot of elements like this. When we have a signal like this, like two triangles, this is a bulb. So it's something that can be locked or open. This is a bulb, a kind of bulb that allows water to go in this direction, but that's all water to go in the other direction. Something like that. Okay, but this is too much. And probably plumbers know more than us about these kind of devices. For us, we need something that heats up water, boiler, and then if it burns gas or other fuel, we need an exhaust in the chimney to get rid of the gases that we have there. And then we need a supply circuit, and then we divide this supply circuit into different circuits, depends on the size of the building. And then we need the same amount of different circuits and it gets to the, so here we have hot water, then the water releases that heat, and then it returns colder, some cold, but not as hot as here, and then it's heated up again, the boiler, and we up the cycle. Very basic. We're going to study two kinds of boilers. Why? There are more. We have different fuels. We have kerosene or propane or whatever. We have oil, but we're going to study gas and pellets boilers. Why? Because they are nowadays, they are the most efficient ones. So you can find other kind of boilers and you need to know them, but nobody. If you want to meet again the passive house standards and zero energy buildings and all that stuff, you cannot install propane or kerosene boiler in your building. But I don't know, by 2050, probably nobody will do it. But nowadays you might find this. But anyway, gas boilers and pellet boilers are the most efficient ones. And with gas boilers, I want to explain the difference between the condenser versus non-condenser gas boilers. The pellets, we know what the pellets are these elements made of wood, smashed wood or ground wood, and then we put everything together and we use this as fuel. But pellets are wood. It's a high performance wood, let's say that. But the difference between condenser and non-condenser gas boilers, it's something that we need to know. And finally, we have solar thermal collectors. If we want to include some renewable energy in this hydronic system, what we have to do is to insert solar thermal collectors. The problem is that in this area of the world, we don't have solar thermal collectors because of the freezing temperatures that we have here. So when we are below 0 Fahrenheit, dealing with solar thermal collectors, it's quite difficult because the water pipes are frozen and then they burst. And so people don't like solar thermal collectors in this area of the world. In Europe, they are mandatory. And they're called climates in Europe. So you can build or you can design a building without solar thermal collectors. Here in the northeast of the United States, nobody uses this kind of solar thermal collectors, but in other countries or even in other areas of the United States, I'm sure that they are mandatory. Okay, so this is we're going to start with the boilers or furnaces. Well, what's the difference between the boiler and the furnace? Well, anyway, so this is a non-condensing boiler, and we're talking about gas. So what's this? Okay, so we have a burner. So in this burner, we have the gas. The gas is the fuel, and then we apply the fire, and we burn gas. And we have a closed circuit like this, and we heat up the water that goes to the circuit. And then we heat this up to a temperature, and here we have a radiator. This is the terminal unit. So this is the energy generator, and this is the terminal unit. A terminal unit can be a radiator, can be a radiant floor, something that uses water. And we release heat in the room, so the water returns colder, and then we heat it up again, and we have the cycle. We are burning gas, so we have to exhaust all the smoke that we generate here, and we get rid of it through tubes. And we need airflow. Okay, so there is no combustion without oxygen. So in this boiler, we need an air intake. We have gas and fuel, but we need oxygen. Because without oxygen, there is no combustion. I'm not. So that's why this is danger. Sometimes we have issues with this kind of boilers, with gas boilers, because they are open to the air. If this boiler is inside, if we have the boiler in the kitchen, and there is something going wrong, if there is a gas leak, we end up having gas inside the room. Gas, this kind of gas, by the way, what kind of gas is this? It's a CH4. So what we call natural gas, or it's a methane. And it's poisonous. We breathe it and we die. Not immediately, that's methane. Die. No, it's not like that. But if we are exposed to, if our lungs are exposed to methane for a long time, we end up dying. Good news. The methane is more dense than air. So if we have a gas leak in our boiler, the air tends to go down. So the gas tends to go down, and our dog will die first. Okay, so if you see your dog or your cat dying without what's going on, probably you have a gas leak in your boiler. So open all the doors, all the windows, and ventilate it. If you don't notice that, the air is little by little filling the room, and when we get to your height, you start breathing it. You don't notice because you don't feel the odor, and if you are exposed to this gas for a long time, especially during the night, you can die. Okay. In addition, before dying of this, you can burst. Okay, so you light a flame or whatever, and the gas is, and then the room is filled up with this methane, with this gas, explodes. So there's a risk nowadays. These kind of burners or furnaces, they take the air. They don't take the air from the indoor environment. They take the air from the outdoor. So if there's a leak, the gas is expelled outside. Okay, so if you buy a burner today, it's very unlikely that you have something like that. But if you burn a house that was built 20 or 30 years ago, and you have a burner like this, there may be some risks of gas leaks. With modern boilers, it doesn't happen. But okay, anyway, this is a non-condensing boiler. And again, nobody uses that anymore because now there's a new technology, which is the condenser boiler. What does it mean? It means that we have this waste gas. So in a traditional non-condensing or non-condenser boiler, and we just get rid of this gas, and that's it. But this gas, it's at a very hot temperature because we're burning the gas here, and we heat up the water, and we get rid of this waste gas. But someone thought, okay, so we're getting rid of something that has a lot of heat inside. So what if instead of having a chimney, we have the gas go through another pipe? Okay, so there are like two coils here. So those are coils. So there are like two coils. The one here in the burner, and there's another one that makes the most of this waste gas. Okay, so as we return the water here, we can make the most of this of the temperature that this waste gas has. It shoots up something. And the water here, then we get rid of it. But we have to heat it up with water. So the burner needs to work less or needs to work less gas because we have to make the most of this waste gas. Okay, so it's very intelligent. And now most of the boilers, gas boilers that we might find are condenser boilers. But again, we need to know it. And we don't know anything. Okay, what do we need? A boiler. Which one? This one. Oh, this is red. I don't like it. We have it in blue. So that's not the right question. The right question is it a condenser or a non-condenser boiler? If it's not condenser, probably it would be cheaper, but it would be less efficient. And the other question that you have to ask, okay, does it take the air from the indoor environment, or does it take the air from outdoors? The one that takes the air from outdoors, it's safer. If you are going to place this in a basement and the basement it's not occupied, that's fine. There is not a risk because nobody will stay in the basement for a long time. But if you have a boiler in your kitchen, make sure that you don't get this air inlet from indoors. So you get it from outdoors. You have the combustion, and if there's an air leak, the air is there. So that's the difference between the condenser and non-condenser boilers. The condenser boilers are the best. So they are slightly more expensive than the other ones, but they save money and they save fuel. And we save fuel, we save money, we save CO2 emissions. So everything is good. Yeah, we have to spend more money, but one of these boilers lasts for 20, 25 years. So it's worth spending a little bit more money because in the long term it will pay off. Pellets. Okay, so pellets, there is no difference between a pellets boiler and what Romans did 2,000 years ago. They burned fuel. And what's the most common fuel? Wood. But this wood is more efficient, well, because it's smashed and it burns better. So as fuel, this is better than. Is it green? Here we have a plant with leaves. Okay, so this is wood, and by burning wood, we emit a lot of CO2 to the atmosphere. A lot. The thing is that a tree, at the same time, during its life, it absorbs all the CO2. Okay, so the balance, it's probably possible. And the amount of CO2 that the tree absorbs during its life, and then the amount of CO2 that it releases when it burns, probably the balance is positive. So that's why we consider that wood, it's well, first it's renewable because we can always plant more trees and we have a renewable source of energy. And then if we consider the whole life cycle of the tree, it's positive in terms of CO2 emissions. But don't think this is okay. We see the pellets. Yeah, it's renewable, and the balance, the life balance or the life cycle is positive. But it doesn't mean that if we burn wood, we doesn't emit any CO2. We emit a lot more than burning gas. Okay. So that's it. And then we have waste, we have ashes, and I don't know, this is very popular, and I think there are a lot of people with this kind of pellets boiler because the fuel it's very cheap and it doesn't depend on someone invading another country or geopolitical issues. So you have a lot of trees around. And if there is a company that runs that tree and manufacture these pellets, you're all set. You don't need to worry about political issues if you have pellet boilers. So the fuel it's quite cheap. But you have CO2, and you need a chimney, and through that chimney you will be emitting gases, greenhouse gases. Finally, the solar thermal panels. We have two kinds of solar thermal panels or solar thermal collectors. We have the heat pipe or the vacuum pipe, and then we have the traditional flat plate collector. Well, if you look at this building from the parking lot, if you look at where the offices are, you will see these kind of solar panels on the roof. They are south oriented, so south is in this direction. So in the roof, they're going down like this. So there we have heat pipes or vacuum pipes. So this technology, we heat up water. Okay, so this is what we do. We heat up water. So that's why we need a hydronic system to make the most of this kind of elements. And the technology, again, this technology, the flat plate collector, people in Rome 2,000 years ago could have done, because we only need pipes, and we only need thermal insulation to keep the heat inside this, and we only need the glass covering these pipes. And then we painted it black to absorb more heat. Okay, but we only need to circulate cold water here. The sun is heating this, it heats up this chamber, and then the water goes to this pipe, and we heat up this water. An inlet and outlet. Instead of burning anything, we have the sun, and we have pipes going in this direction. The sun hits on the pipes, they are painted in black, they absorb more heat, and they heat up the water inside. Quite easy. The problem is freezing. We are below the freezing temperature. It's in Celsius, it's 0 Celsius. In Fahrenheit, I think it's 32 or something like that. So if we are below 32, we have freezing issues. Can we have the temperature below 32 here for a month, a year? So there are solutions to this. So we can have an anti-freezing, as we have in the cars as well. And we can, that if we mix water with the glycol is the other fluid that we use to mix up with water to avoid freezing, then the effectiveness, it's less efficient in terms of heating up. Okay. Basically, people don't use it here because the risks of freezing, it's too much risk, and people don't want to run risks. So this is the flat plate collector technology. The heat pipes technology, it's more advanced, and the Roman people, I don't think they would be able to do it, because we need two cylinders, two glass cylinders, and between these two glass cylinders, we have vacuum. Okay, so we don't have air, we don't have any gas, so it's vacuum. And vacuum, it's the perfect thermal insulator. But we need to produce vacuum between these two parallel cylinders. How can we do it? I don't know, but we can do it. I mean, there are companies that can do this, but manufacturing this is quite complicated, because first you need to get the double glazing, then you need to extract all the air or gases that we have this, we have vacuum, and then we have a pipe with an absorber plate. So this is the same, we need a pipe. And here we don't have water. Here we have a fluid, and the water is here. The water is at the top. Okay, so this is where the water is heated up. And here we have, in this pipe, we have the heat transfer fluid. It's not water, it's heat transfer fluid. So when the sun is heating up the fluid here, the fluid goes up. So the hottest fluid is here, and then we have water in this direction. So if the water, as it goes through, it's involved with the hot fluid, it heats up, and then when this fluid cools down, it goes down again. So we have this cycle, and we heat up this fluid, it goes up. It heats up the water, then the fluid goes cools down, and it goes down. So we have this. So it's complicated. It's much more efficient than the flat plate collectors. They are more expensive, but they have another advantage. It's that they are beautiful. Okay, so looking at these transparent cylinders, that's beautiful. Those elements are ugly and nobody likes them. But anyway, again, you won't find this kind of solar collectors or solar thermal panels in this area, but In other areas of this country and in other countries, they are almost mandatory. And you want to generate hot water, you need to place these kind of elements, especially on the roof. And then you need to connect this. We have exactly a hydronic system. It's always the same. We have something that heats up water. In other cases, it's a boiler or turbine, whatever. In this case, it's a solar panel. And then we have a supply and return or inlet and outlet. We always have the expansion tank. We always have a circulation pump. And in this case, we need a tank. So we have a tank here. So that tank, that's like the cylinder that we have over there. It's a hot water tank. So we can connect this to a boiler, we can connect this to solar panels or whatever. So we heat up water in this tank, and then we have we can use this tank for heating system or domestic hot water or whatever. But a hydronic system, it's always the same. Okay? Circulation pump, expansion tank, something that heats up water, and a tank. Yeah. And then from this tank, we move this water to the rest of the house. But it's something very basic. Okay, so here we have this schematic view. We have solar panels here, solar thermal collectors. This is the inlet circulation pump. Here we have the expansion tank, heat up water. The water is hot. We take this into the tank, and then from the tank, we go to, this is the domestic hot water, the sink, the shower, or whatever, or we have another circuit that goes to the radiant floor. Usually, the temperature that we have in this, in the sink or in the shower, and the temperature of water in the radiant floor is different. So I wouldn't do this. So here it looks like I have the same circuit for the radiant floor and for the water. Usually the temperatures are different, so I will need two different circuits. But other than that, that's it. And if you don't want these collectors and you want the boiler, you add here a boiler and you have the same system. So you have a boiler, the tank, and then either the hot water or the radiant floor or radiators or whatever. So here, when it comes to solar thermal panels, we always need a backup. Okay, because what if we don't have sun? Today we don't have sun. If we don't have sun, we don't have hot water. So we always need a backup. So we can apply boiler here. So in the event of not having any sun, we can run the boiler. So for sunny days, probably we don't need the boiler, but for cloudy days, we will need the boiler. So that's why we have this tank here in the middle. So this tank can be heated up by solar collector or by boiler. Okay, so this sounds more, this looks more reasonable. We have a tank here, we have the solar thermal collectors connected to the tank, and we have the boiler connected to the tank as well. And then this is the water, the hot water supply, whatever. Okay, so we do need a backup heating. So connecting a boiler to the tank. So I wouldn't go 100% solar with solar thermal collectors, because if we don't have sun, we don't have hot water. Okay, so use a backup plan like a boiler. Okay, that's another issue. And well, you see here we have different coils. Okay, so we have a coil that releases heat here, and then it goes back. Releases heat here, and then it goes back to the solar collector again. And then the boiler is usually connected to the top of the tank. Why? Because we have to get the water from the part of the tank in which the temperature is the highest. And where is it? It's at the top of the tank. Okay, so we start heating up things at the bottom of the tank. So the hot water will go up If it's not enough, we apply the boiler, and then we have the right temperature, and then that's the temperature that we need for the shower. Okay, but as you can see, there are two closed loops, one and the second, and here we have the coil to release heat to the tank. Temperatures are relevant. There's a tank. Okay, there's a tank here. So from the top of the tank, we need the hot water supply. Okay, so we need the hot water supply. This can be the shower. And the temperature here in the domestic hot water, the temperature should be at least 140 Fahrenheit. If not, okay. Nobody can cope with 140 Fahrenheit. So if we open the hot water in the shower and the water is at 140, you get burned. And so you mix this with cold water. And at the end, the water in the shower, we have something at 140 with cold water. No, X, but let's say 100 Fahrenheit. Something reasonable. But we need 140 to kill it's a bacteria named after Roman legions, because when they went to conquer the rest of the world, they died because they drank water that it was warm. So when the water is warm, it's prone to generate this bacteria, and it was so we need to burn to raise the temperature of that water at 140. We kill the bacteria. So that's why we cannot go with the 140. That is this circuit, because it's in contact with us, our skin, and we can even drink it. So we need to heat it up to 140. And then we have to reduce that water by mixing it with the cold water. Okay? But we need to kill this bacteria here. So the temperature that goes out from this tank, it has to be at 140. But if we have another circuit with radiator or radiant floor or whatever, the temperature here probably can be 100, 120 Fahrenheit. The temperature through radiators or radiant floors. Okay, so we when we have a tank like this, we always have like different connections. So we can connect this at a temperature, and we can connect this at a different temperature. And then this is the circuit that we have inside the building. What do we have outside the building? So we can connect this to the solar terminal, solar collectors, or we can connect this to the boiler. Okay, so depending on here, we have different sensors, and we have different temperature. So when the temperature is close to 140, we use this circuit. The temperature in this tank is 120, then we use this circuit for the. Okay, so it's quite complicated, but it works. Okay, but the temperature in the tank it's not the same temperature. The hottest temperature is always at the top, and from this top connection, we get the domestic hot water. And then at some points, we have other temperatures, and then we get the temperature that we need for the radiant floor, radiator, or whatever. In this case, We are not using this for the heating system. It's just for the shower. Okay. And those are the distribution devices or the terminal units. So we can have radiators. So we circulate hot water here, we release heat, and we have these kind of radiators. We have the radiant floor. We can have radiant panels. Okay, so the radiant panel is the same as the radiant floor that involves. And then this is the new thing that I'm going to explain today, the fan coil unit. A fan coil, you might mistake a fan coil for something like this, like a split indoor unit, because they look alike, so they are the same. But the fluid circulating through this is this refrigerant fluid that we saw last week. Here we have water. Through the fan coil, we circulate water, and it can be hot water for heating or cold water for cooling. Okay, so a fan coil, we have a fan that moves the air, and we have a coil that circulates fluid, water. Okay, and we have in the fan coil, we always have four. 1, 2, 3, 4. You see that we have the cooling coil, which is the blue one, and the heating coil, the red one. Okay, so we have inlet and outlet for cooling, inlet and outlet for heating. It works. It's like a small air handling unit. Okay, so the air handling unit, we have a lot of things there. We have heating, we have cooling, and we have ventilation because it takes fresh air from the outside. With a fan coil, we don't have ventilation. So we just cool down or heat up the air inside the unit, but we don't have access to the outdoor air. Okay, but the fan coil, it works as an air handling unit, but it doesn't get a fresh air from outside. So that's the difference between fan coils and air handling unit. But a fan coil, believe me, if you look at fan coils, it looks like this. Okay, so if you look at this, there is no difference. And I can tell that this is not a fan coil because we have refrigerant fluid. If there was water, it would be a fan coil. If we have refrigerant fluid, and we have the split unit with a heat pump. Well, that's important. I told you that there are different circuits. Okay, so at some point in a mechanical room, we have this. And when we have something like that, it's like the main pipe. Okay, so directly from the boiler or from the tank, we have a pipe that is thicker than others. And then we have different circuits. So this is a heat pump, circulation pump, sorry. This is another one. And that's another one. At least if we have 3 different floors, this is the first floor, the second floor, and the third floor, we might need 3 different circuits. And then if we have a very big building, we can have different circuits for the first floor, different circuits for the second floor. So what's the name of this? The name of this is a manifold. Okay. So in these mechanical rooms or big buildings like this one, the inlets and outlets from the boiler or from the tank, we have like a very thick pipe, and from that thick pipe, we have these circulation pumps, and then we pump the water throughout the building. And then we have to collect. Okay, imagine that from this one, we have radiators, radiant floors, or whatever. And now we collect this in another manifold. Return. And now that goes to the boiler. Okay, so we collect as many circuits as we have here. If there are 4 supply circuits, then I will have 4 return circuits, and then I will get all these pipes to the. And those are circulation pumps. So every time we have a circle with a triangle on it, this is a circulation pump. In a single family house, we don't have this, because probably how many circuits do we have in a single family house? 2. If we have 2 circuits, we just have 2 vertical pipes, and that's it. But if we have 10, 20 different circuits, we have these manifolds, and before the water pump or the circulation pump, we always have a valve. Why? Because if there's an issue with this circuit, imagine that we have to replace this radiator. If we have to replace this radiator, we have to cut off the water here. So we cut off this circuit, and now we can replace the radiator. Or if we want to replace this water pump, maybe it's broken, we cut off here, we cut off here, we replace the pump, and then we put another one, and then we open the valves again. Okay, so valves are always important because it helps us control the circuit. Okay, so we have a valve here. So if there's an issue with this circuit, we cut off the water here, that's it. And then we have valve in the return as well. We always have an expansion tank, always. And this is a hydraulic separator. The separator is in drain valve. Okay, so sometimes with water we can have solid particles. So those solid particles, they weigh more than water, and we need something like this so that the solid particles are here, and then we can remove. Yeah, we can do that. Okay, but the basic elements are always circulation pumps, as many circulation pumps as circuits, and we always need an expansion tank. And then we need valves, and valves are important, so the more valves, the better. But they are very expensive, those valves. A valve like this can cost like $20. Okay, so the more the better. But we can have so before every when we have an element or a radiator or whatever, we always need a valve. So if there's something here, I can cut off these valves and replace that element. And if there's another radiator here, I will have another valve, so that I can replace those elements without affecting the rest of the circuits. Okay, but what kind of elements do we have? We have manifolds, pumps, water pumps, circulation pumps, expansion tanks, valves, so at least we need all these elements with tanks. Okay, so all these together make up what we call a hydronic system, because it uses water. And this is what a mechanical room looks like. So those are the pipes, those are the water pumps, these are bulbs, these things here. So painting the pipes, well, it helps because we can have red pipes for hot water, blue pipes for cold water, yellow, green for other things. Okay, but getting organized, it's important because look at this in buildings like this one. We need a huge mechanical room because those pipes and pumps and those elements take up a lot of space. Okay, so and if we don't have a code, here we have these stickers and we can tell where the refrigerant, hot water in a mechanical room. Again, if nobody tells you what it is, you're lost. If you have to, because the company will install all this and they will go. So you need instructions, and you or other building manager enters here, and all the pipes are the same color, and you don't have any specification about the inlet, outlet, or supply or return or whatever, and you get lost. Okay. So those are mechanical rooms, but now again, we have abstraction, we have a circle and a triangle. This is a pump, but what is a pump in real life? Something like this. Oh, and that's interesting because you see that here we have two parallel pumps. So when the building is really big and we can't afford having a building without water or without a heating system because a hospital or whatever, we always have two parallel pumps. So we have something like this. And then they connect again the same. Why is that? And we have the bulb here, another bulb there. Okay, we can interrupt the water supply, again, because it's a hospital or something. If this water pump stops working, then we cut off this one, and then we have the other one back. And then this starts working, and after I don't know how many hours, this stops working, and then we have to place the other one. Okay, so in these mechanical rooms, sometimes you find two parallel water pumps. This is because we can stop the circulation of this water, and then we have just a backup. If this stops working, the other one starts working immediately, and then you have to repair this one. Because those pumps don't last forever. They have so they have a limit, and that limit might be, I don't know, 3,000 hours. Okay, 3,000 hours. If you are working with this pump 24 hours a day, 3,000 divided by 24. So those are the days that the pump will last. If it's working only for 10 hours a day, then the pump lasts more. Okay, so we tend to think, okay, start pumping and I don't know, 24 hours. We can save energy, we can save money that the pump, because those pumps are quite expensive, especially the big ones. If we have sensors and we have schedules and this is not working 24 hours a day, we save energy, we save money because we are not running the system throughout the day. Okay, so this is it. Those are hydronic systems. First, we have the energy generators, boilers, condenser, non-condenser boilers, pellet boilers. If we want renewable energy, solar thermal collectors, heat up water. Then terminal units, radiators, radiant floors. Radiant panels are not very popular, but we can apply the same principle in walls, and fan coil units. And that's it. Okay, so we have to generate energy in hydronic systems. We transport this energy with water. So we need to heat up water. Renewable solar panels. If we don't use renewable energies, let's use a fuel that goes well in terms of CO2 emissions. Wood, it emits a lot of CO2, but if we keep in mind the total life cycle of the tree, then the balance is positive. It absorbs more CO2 than it emits when it burns. Okay, we can accept that. Gas is a good option, especially if we use the condenser boilers, because the gas, the CO2 emissions when we burn methane are not as much as the CO2 emissions when we burn oil or propane or other gases. Okay, so methane is the best in terms of CO2 emissions. That's why gas is mainstream in every heating system, especially in cities. In the 19th century, when cities started to grow a lot, especially after the Industrial Revolution in London and where the Industrial Revolution took place, the air of the cities was terrible because they were burning coal, because this is what they had. So they burned coal and the air was terrible. We have been substituting, especially in cities, we have been replacing the coal boilers by methane or gas boilers, and now things are much better. But if we don't want to burn anything, we can use heat pump, as we saw last week. And with heat pumps, we use electricity. So by using electricity, we can heat up water, we can cool down water, so we can apply to this hydronic system. Here we have a boiler, but if we have a water or an air to water heat pump or a water to water heat pump, we can use a heat pump as a part of a hydronic system as well. Any questions? It's too much information, I know, but you need to know